In the last video, we started talking about redox reactions and how to use oxidation numbers to determine who's being oxidized and who's being reduced. So here's an example of how to determine who's being oxidized and who's being reduced. We're told when powdered aluminum metal is mixed with pulverized iodine crystals and a drop of water, the resulting reaction produces a great deal of energy. The mixture bursts into flames and a purple smoke of I2 vapor is produced from excess iodine. The equation from the reaction is, so here's our reaction. Now first I need to determine oxidation numbers before I can determine who's oxidized or reduced, or who's the oxidizing and reducing agents. So aluminum is starting out as a solid. It's an element in elemental form, so it's going to be 0. I2 is also an element, so it is a 0 as well. Over here we've got an ionic compound, aluminum triiodide. Aluminum in an ionic compound is a +3. Iodine in an ionic compound is a -1. So aluminum is going from a 0 to a +3. He's becoming more positive, so he's being oxidized. Iodine is going from a 0 to a -1. He's becoming more negative. He's being reduced. So aluminum is oxidized, which means it's the reducing agent. Remember, they're opposite each other. Iodine is being reduced, which means it's causing aluminum to be oxidized, so it's the oxidizing agent. Okay? That easy. So here we've got two different reactions that we're solving. This reaction takes place in 2 steps. Okay? So the first step is we've got lead-2 sulfide reacting with oxygen to form lead-2 oxide and sulfur dioxide. Okay? So we want to determine who's oxidized, who's reduced, who's the oxidizing agent, and who's the reducing agent. Okay? So here's what we're going to do. Okay? PbS is an ionic compound. In the ionic compound, sulfur has a charge of -2, so lead's going to be a +2. Oxygen starting as an element, elements are 0. Over here, lead is still in an ionic compound. Oxygen is a -2 in the ionic compound. Lead will be a +2. Sulfur dioxide, oxygen still a -2. I have 2 of them. 2 times 2 is 4, so I need 4 positives. Okay? So I need to figure out who's changing. Oxygen is going from a 0 to a -2, and sulfur is going from a -2 to a +4. Okay? So oxygen is becoming more negative. He's being reduced. If oxygen is being reduced, that means he's the oxidizing agent. Sulfur is going from a -2 to a +4. He's becoming more positive, so sulfur is being oxidized. Since he's being oxidized, he's the reducing agent. So once we make our PbO and our CO, we're going to, or our PbO, lead-2 oxide, we're going to react it with carbon monoxide to make lead and carbon dioxide. So take a second, determine the oxidation numbers for all of these. Who's being oxidized, who's being reduced, who's the oxidizing agent, and who's the reducing agent. What you should have seen, we already did oxidation numbers here. Lead is a +2, oxygen's a -2. Carbon monoxide, oxygen's a -2, so carbon's a +2. Lead's an element, so it's 0. Carbon dioxygen, oxygen's still a -2. There are 2 of them, so 2 times 2 negative is 4, so I need 4 positives. Okay? So I have lead going from a +2 to a 0, carbon going from a +2 to a +4. Carbon is becoming more positive. He's being oxidized. Lead is becoming more negative. He's being reduced. Since carbon is oxidized, he's our reducing agent. And since lead is reduced, he's our oxidizing agent. So, somebody is always oxidized and somebody is always reduced. If somebody's gaining electrons, somebody else has to lose electrons. And we can use this concept to balance redox reactions. Here's the way this works. I've got my equation. Now this one's nice. We've got monatomic ions, so it's really easy to track charges. What I'm going to do is I'm going to break this into 2 half reactions. So here's what a half reaction is. I've got Ce4+ going to Ce3+. That would be one reaction. I've got tin 2+ going to tin 4+. That would be my second reaction. Okay? Now they're half reactions because it's only half of what's going on. So Ce is a 4+. He's aqueous. He's going to Ce that's a 3+. It's also aqueous. Tin is a 2+ aqueous, going to tin that's a 4+ aqueous. Now, I also have to show how the electrons are changing. So, in order for this to go from a 4+ to a 3+, I'm becoming less positive, more negative, which means I have to gain electrons. And to go from a 4 to a 3, I need to gain 1 electron. So I put my 1 electron as a reactant because 1 electron, 1 negative, plus 4 positive will give me 3 positive. Okay? Down here, I'm going from a 2 to a 4. I'm becoming more positive, which means I'm losing electrons. My electrons will be products. Now to go from a 2 to a 4, I need 2 electrons. And the way I can double check this, 4 positive plus 2 negative gives me 2 positive. Okay? Now in redox reactions, somebody always has to gain electrons. Somebody always has to lose electrons. If I have somebody being oxidized, I have to have somebody being reduced. Now, I can't just go around with random numbers of electrons. My electrons have to cancel out. So, 1 electron here, 2 electrons here. I need to make those the same. So I need to multiply this one by 2. Well, I can't just multiply my electrons by 2. I need to multiply the whole thing by 2. Okay? So here's the way it would work. I'm going to have 2 times 1 is 2 electrons, plus 2 times 1 is 2, Ce4 pluses. Okay, this is a reactant, so I'm going to put it in, and I didn't mess with that, so it stays the same. I go to the other side. 2 times 1 is 2 Ce3 pluses. I didn't miss with this one, so it's just an Sn4 plus, and I had 2 electrons on this side. Because my electrons are the same on the left and the right, I now have a balanced chemical equation. I cross those out because they cancel out. They're the same on the left and the right. And so my complete balanced well, not my complete, but my balanced chemical equation for this redox reaction would be 2Ce4 plus Sn2 plus forms 2Ce3 plus and Sn4 plus.